My name is Witowski, and this is my Lab 3 video report on black holes and orbits. In this lab, we use both computations and Newton's second law to analyze the orbital motion and achieve our two main goals, which one was to determine the mass of a black hole by analyzing the motion of a star orbiting it, and two, to simulate the motion of a spaceship orbiting both a planet and a moon without crashing. As a preview of the results, we found that the mass of the black hole to be approximately 1.5 times 10 to the 34th kg, and in the second part of the lab, the velocity was 0 in the x direction and 1350 in the y direction. Now on to the physics principles. The main physics principle that was used in this lab was Newton's second law, F net equals dp over dt. This means the force acting on the objects is equal to the rate of change of its momentum. Then, using the velocity data from the trajectory, the program was able to calculate the initial momentum and final momentum, change of momentum, and rate of change of momentum, otherwise known as dp over dt. According to Newton's second law, this quantity is equal to the net force acting on a star. Since the only force we assume is gravity from the black hole, we can use the gravitational force equation F equals gmm over r to the second. It is by rearranging this equation that we are able to solve for the mass of the black hole. Just as a quick note, the system is the star and the black hole, and the surroundings are everything in the universe and the universe itself. There is also the information that we were given beforehand listed below. In the code, I first calculated the velocity of the star using the position data and the time interval. Then the code calculates the initial and final momentum vectors using p equals mv. Next, it computes the change in momentum divided by the time, which gives dp over dt, and therefore the net force acting on the star. The program also calculates the parallel and perpendicular components of this force relative to the direction of momentum. Finally, using the magnitude of the net force and the distance from the black hole, the program calculates the mass of the black hole during each iteration of the loop. Since each iteration gives a slightly different value, we estimate the black hole mass by averaging these results. As you can see, the estimated mass of the black hole was approximately 1.5 times 10 to the 34th kg. This was the value calculated repeatedly during the simulation and averaged to produce a single estimate. Well, what does this mean? The net force and the rate of change of momentum represent the same physical quantity according to Newton's second law, but they describe it in slightly different ways. The rate of change of momentum describes how the motion of a star is changing over time based on an observable data like velocity. The net force describes the physical cause of that change in motion. When broken into the parallel and perpendicular components, the parallel component changes the magnitude of momentum, and the perpendicular component changes the direction of momentum. In orbital motion, most of the force is perpendicular to the motion, which is why the star moves in a curved path around the black hole. In part 2, we created a system that had a spaceship and a moon, and the surroundings were the star and the rest of the universe. Listed below are our givens. The goal was to find initial velocity for the spaceship that would allow the orbit of both the moon and the planet to go around without crashing into each other. The simulation used gravitational forces between all objects and applied Newton's second law to update the motion over time. The gravitational force between the two objects is calculated using F equals gmm over r to the second. In the simulation, we calculated the gravitational force on the moon from the planet, the gravitational force on the moon from the spaceship, the gravitational force on the spaceship from the planet, and the gravitational force on the spaceship from the moon. These forces were added to find the net force on each object. Using Newton's second law, we updated velocity and position at each timestamp using numerical integration. In the results, I found the velocity to be 0 in the x-axis and 1350 meters per second in the y-axis, and mine wouldn't let me go past 700 hours, but theoretically it should have gone all the way around without crashing. And here are the possible sources of error: ignoring the surroundings, the average is not completely accurate, which is in part 1, assuming point masses, assuming circular orbit, and rounding inaccuracies. Alrighty, what if we wanted to predict the motion of the entire system? Then we would need to include all gravitational interactions between every single object. That would include things such as the black hole, the star, the planet, the moon, and the spaceship. Each object would exert gravitational forces on every other object, but at some point, some of those interactions would become stronger than others. For example, the black hole would dominate the motion of the star, while the planet would dominate the motion of the moon. These interactions simplify the model but complicate the simulation and would change the results, basically. Thank you for watching.